So here we have an issue where we're trying to find out how far away this ball landed from the edge of this ramp. So this is really fundamentally a projectile motion problem. And so it's a motion equation problem. For projectile motion problems, I always make a motion equation data table for each direction, the x direction and the y direction. So let me take a moment to do that and fill in the details of what we know here. Looking at the y direction first, it seems as though the initial position is 2 meters. It lands on the ground, so final position is 0. Now the initial y velocity is 0, and the reason for that is because it tells us that the end of this ramp is horizontal. So at the end of its trip, just before it goes into the air, it's moving horizontally, which means its y coordinate is not changing. It has 0 y velocity. Of course, its acceleration is negative 9.8 meters per second squared. Let's look at the x direction. Well, there's no reason we can't say the initial x position is 0. Final x position, that's ultimately what we're looking for. The initial and final velocities in the x direction are always going to be the same because there's 0 acceleration in the x direction because there are no x direction forces. So typically, with a projectile motion problem, we're going to solve for time in one data table and use that in the other one. And we have enough information to solve for time over here using yf equals yo plus vot plus 1 half at squared. By the way, I'll just show you a little shortcut here that I use sometimes. If we fill in some details here that the final position is 0, the initial position you could simply call the height. That's how high it is above the ground. The initial velocity is 0, so that part of the equation is 0. The acceleration is negative g. G stands for 9.8, and the direction is negative, so negative g. We have t squared there. So if you simplify that for time, you get square root of 2h over g. You're not going to see that on your formula sheet because it doesn't work all the time. It only works when the initial y velocity is 0. So be careful about using this. You can only use it when the initial y velocity is 0. However, if that's the case, then it's a good thing to have in your back pocket because it's quick and easy to use. So square root of 2 times 2 over 9.8. Let's see what that gives us. So that's going to be 4 over 9.8, and I'm going to take the square root, and it pretty much rounds off to 0.64 seconds. So that's our time for this trip in the air, 0.64 seconds. And again, our goal is to figure out how far it goes, xf, but we're going to need to figure out how fast it was moving the moment it came off the track in order to answer that question. So that's why we're going to need to look at this part of the trip here. And this problem where we have a ramp, so first of all, since it's not in free fall, the acceleration is not 9.8 meters per second squared. And even if we did have some sense of the acceleration, that acceleration is constantly changing because of the curvature here. Sometimes it's a high acceleration, sometimes it's a low acceleration. This is an equation that's impossible, really, to solve with motion equations. But since we have a changing height and we want to know a velocity, that's a classic situation where law of conservation of energy will help. So let's do it that way. I think it's really the only way that we can do it. I'm going to say that A is up here at the top. Let's say that B is down here where it's coming off the ramp. And then let's fill in the details. At A, we have gravitational potential energy, m times g times 6 meters high. Starts from rest, no kinetic energy at A. No non-conservative forces on this trip. Non-conservative forces are forces that don't create potential energy. The only force that's really doing work here is gravity, and that does create potential energy, so gravity is a conservative force. On the other side, we have m times 9.8 times 2, because again, I want to know the velocity right here. And then we have kinetic energy, and here's where you have to be careful. This is a rolling object, and when something rolls, two things happen at once. Just draw a little illustration of that here. On the one hand, it's rotating, and so we need to use 1 half I omega squared. But on the other hand, the axis of rotation is not staying in place. The axis of rotation itself is moving forward, and that's called translation, and that's 1 half mv squared. So anytime the axis of rotation is not fixed in place, anytime the axis of rotation is moving, you need to do both 1 half I omega squared and 1 half mv squared. Now, this is going to take a little bit of substitution. What I want to do is just get down to one variable here. I don't want omega and v, I just want v. So what can I substitute in here? Well, first of all, I want to make a substitution for I, the rotational inertia. They did tell us it's a solid ball. So there's a well-known formula for the rotational inertia of a solid ball. You need to look that up in your textbook or online. It turns out to be 2/5 mr squared. And then the angular velocity, that's in radians per second. But we can calculate that from the linear velocity by taking the linear velocity and dividing by the radius. So that's really the conversion between angular velocity and linear velocity. Omega is equal to v over r. And so that actually allows the r squared to cancel out, and a half times 2/5 is 1/5, and then mv squared, plus over here 1/2 mv squared from the translational kinetic energy. So these two can be combined. They have a common denominator of 10, and so you end up with 7/10 mv squared. Let me just bring down the other elements that I sort of left behind. Here we had m times 9.8 times 2, and on the other side of the equal sign we had m times 9.8 times 6. And now we can see that the masses all cancel out, and it's just a matter of calculation here. So 6 minus 2 is 4 times 9.8 times 10 divided by 7, and I'm going to take the square root, and I get 7.48 meters per second. So the speed is 7.48 meters per second when it comes off the ramp. That's what we needed for our x data table. And so now we can use this equation, xf equals xo plus vot plus 1/2 at squared. That's really the only equation you ever need for the x direction. It's the one I always use. So xf equals 0 plus 7.48 times 0.64 plus 1/2 0. Doesn't matter what the time is because of that 0 there. So it's really just 7.48 times 0.64, and I'm getting 4.78 meters for the final answer.